Okay, so in this problem, we have a guy on a magic carpet. He's holding a 5-kilogram bowling ball just out at arm's length, and he is at a distance h above the ground. So what we want to find out is when he drops this bowling ball, what is the velocity going to be when the bowling ball hits the ground? Now he's not going to throw it, he's just going to hold it out, drop it, so our initial velocity is going to be 0. Also, we're going to neglect air resistance for this case. So there are a couple ways to solve this, but one of the fastest ways that comes to mind is using the work energy theorem. So the work energy theorem says that work is going to be equal to the change in kinetic energy, right? So kinetic energy, I know that's in terms of the mass and the velocity, so that's a pretty good thing for me to assume I can find the velocity from that. Now the work, what is the work in this case? Well, work is going to be equal to the integral of the force dot dr. So it's just the force along the direction. Now, in the case that you have a constant force, this reduces to the more usual case that you're probably more familiar with, which is just Fd. And this is in the case that you have a force that's in the same direction of motion, and it's a constant force. And this is going to be equal to delta Ke. So really quick, what is delta Ke? It's going to be the final kinetic energy minus the initial kinetic energy. Well, we know the initial kinetic energy is 0 because there's no velocity. Velocity is 0. Now, what is the final kinetic energy? Well, I'll call that 1/2 m times Vf, Vf for final velocity, Vf squared. Now, what is F times d? Well, our force here, the only force that's going to be acting on this, since we're neglecting air resistance, is going to be gravity. So that will be mg h, h for our distance, and the thing with g and h. So gravity is normally denoted as a negative acceleration, so negative 9.8. Now h, since we're going to define downward as our negative direction and up would be positive, since this thing is going to be going down, we'll say that h is negative because it's going to go down negative h meters. So what you end up really getting, this is equal to m times negative g times negative h, but it ends up just being mgh. So all is good. So let's bring this down here. We'll say mgh is equal to 1/2 m Vf squared. So you can go ahead and see that these m's are going to cancel. And now what I'm going to do is I'm going to multiply by 2, and then I'll take the square root. So this gives me, I'm going to bring the Vf to the left. So I get Vf is equal to the square root of 2gh. Now remember that when you take the square root like this, you're going to get plus and minus. But we're going to want to take the negative root because we know that the velocity is going to be downward, and we define downward as negative. So we will take negative square root of 2gh. So we can use this to find an approximate velocity for this bowling ball at any height. Now I say approximate because you need to remember how we get g. So if we go back to Newton's laws of gravitation, you have F is equal to negative g times big M, which is the mass of the Earth. Little m is going to be the mass of the bowling ball in this case, divided by r squared. And the negative just means that the force is directed towards the center of the Earth, which would be downward. Now, if you remember that F is equal to mass times acceleration, we can rewrite this as ma equal to negative g over r squared. Now these m's cancel, and you're left with a is equal to negative gm over r squared. Now, you're probably wondering where g comes from and how it's relevant. Well, we get g by setting the radius equal to sea level. So if I rewrite this, I can say g is equal to negative g, big G, m, mass of the Earth, divided by, now instead of r squared, I'm going to call it s for sea level, but it's still a distance. So this is s squared. So now this gives us g, but you can see that g is only really constant or doesn't vary much when our heights are about sea level. So this formula we have here will be relatively accurate for things that are near sea level. But what happens if we have something that is very high above sea level? So let's say that our guy on the magic carpet decides to fly up and visit some astronauts on the International Space Station. And while he's there, he's going to walk out onto one of the modules, and he's going to hold the bowling ball out, and he's going to drop it. So what happens then? Well, in that case, G, or we can say the acceleration due to gravity, or the force due to gravity, varies as this bowling ball approaches the Earth. So how would we find the exact final velocity if we have a varying force of gravity? So to do that, we have to go back to the integral definition, and we'll start from there. So we already know what F is. F is negative G times big M times little m divided by r squared. So we can take this, and I'm going to start right here. So this is the integral of negative G, big M, little m, divided by r squared dr. Okay? Now we have to think about bounds. What are our bounds? Well, what is our initial height? So we'll be at sea level plus some height, right? So we'll call it s plus h. So we're going to start at s plus h, and then we'll end up at s. Okay? So there's a couple things I'm going to do to this to make it a little bit easier to work with. Let's go right here, down here below. So I have a negative. When I have a negative like this, I can use that to flip the bounds of my integral. So I'll turn this into s plus h, then s. Now I can also take these constants, g, m, and little m, outside. So this becomes g, m, m. And 1 over r squared, I'm going to rewrite that as r to the negative second. Okay? Now, we're going to use the work energy theorem again. And we already know what our change in kinetic energy ends up being. It's just 1/2 mvf squared. So I'll put this equal to 1/2 mvf squared. And you can see again that the little m's, the mass of the bowling ball, cancel out. So I'll just put a line through those. Cool. Now what I want to do is, let's go ahead and evaluate the integral. So what is the integral of r to the negative second, or 1 over r squared? Well, that just turns out to be, it's going to be negative r to the negative first, which would be the same as saying negative 1 over r. But I'm going to write it as negative r to the negative first. So this will be negative r to the negative first. And then one of our bounds, we evaluate at s and s plus h. And this is equal to 1/2 bf squared. Now, I'm just going to go ahead and multiply the 2 over. And I'll also evaluate the bounds at the same time. And we'll leave the square on the bf for now. So this becomes 2gm. And I'll put this in square brackets. Negative r to the negative first. And we will start with s plus h, our upper bound. So negative s plus h to the negative first minus a negative s to the negative first. And this is equal to vf squared. Okay? Now let's go ahead and simplify a little bit. The negatives cancel, and we will get a 2gm. This will be s to the negative first minus s plus h to the negative first. And let's go ahead and take the square root of the vf like we did before. So vf, and then we have this right here. Okay, so now we have 2 expressions for our final velocity of something dropped from a height with the initial velocity of 0. So this is the exact answer we found using the integral definition of work. And the vf equals negative square root 2gh is the approximation we made using g. Oh, and also remember, we will choose the negative root here since we know it will be a downward velocity. So now the question is, was it worth the work? How different are the 2 answers? So if we use the approximation and we say the height of the, if I'm remembering correctly, the height of the ISS is 408,000 meters above sea level. So I will say, I'll call this V approximation. That is going to be 2,828 meters per second. Now, that's really fast. It would not be going this fast in real life. It would reach terminal velocity and would be significantly slower than this. So now let's look at the more exact answer. This is also a negative velocity because it's going to be going downwards. So what is the exact answer? So if I use the distance for the Earth at sea level, which is about 6,371 kilometers, and then the distance for the ISS that we already said, and I plug all my numbers in, I plug in the gravitational constant, and I plug in the mass of the Earth, that's going to give me 2,744 meters per second. So this is a difference between the exact answer and the approximate answer of, this is also negative, this is an 84 meter per second difference. Now to put that in perspective, 84 meters per second is about 188 miles per hour. So at large distances, you can see that we actually start to see a difference between this approximation and the exact answer.